Hello and welcome to Nighttime Science. Close your eyes, let your shoulders drop, unclench your jaw, let the tension drain out of your body, flowing down through your arms, through your legs, and into the ground beneath you. You are safe. You are still. The quiet forces beneath our feet. Beneath the surface of our planet, where no human eye can directly observe, the Earth carries on a conversation with itself that has continued for more than 4.5 billion years. This dialogue unfolds in the language of heat and pressure, of flowing rock and shifting continents, of forces so gradual they escape our notice in the brief span of a human lifetime. To understand volcanoes and earthquakes, we must first understand that our world is not the solid, unchanging sphere it appears to be. Instead, Earth is a dynamic body constantly reshaping itself through processes that occur on timescales far beyond our everyday perception. The Earth beneath your feet is composed of distinct layers, each with its own character and role in the geological processes that shape our world. The outermost layer, the one we walk upon and build our civilizations across, is called the crust. This thin skin of rock varies in thickness from place to place, measuring between 5 and 70 kilometers deep, depending on whether you stand on oceanic floor or continental land. The oceanic crust, younger and denser, consists primarily of a dark volcanic rock called basalt, which forms continuously at mid-ocean ridges where tectonic plates pull apart. The continental crust is composed largely of lighter rocks like granite and its metamorphic cousins, giving the continents their relative buoyancy upon the layers below. These lighter continental rocks contain more silicon and aluminum, while the heavier oceanic crust is richer in iron and magnesium, differences that reflect their different origins and histories. Below the crust lies the mantle, a vast realm that extends downward for approximately 2,890 kilometers. The mantle makes up roughly 82% of Earth's total volume, and while it consists of solid rock, this rock behaves in ways that seem contradictory to our surface-dwelling experience. Under the immense pressures and temperatures found deep within the Earth, rock can flow like an extremely viscous liquid over geological timescales, moving just centimeters per year but never ceasing its slow, patient motion. The temperature in the mantle increases gradually with depth, starting at around 700 degrees Celsius near its upper boundary with the crust and rising to approximately 3,700 degrees Celsius near its lower boundary with the outer core. The mantle itself divides into regions of different behavior and character. The uppermost portion of the mantle, together with the crust above it, forms what geologists call the lithosphere. This is the rigid, brittle outer shell of our planet, extending down to depths of approximately 100 to 200 kilometers, though this depth varies depending on location and the age and thermal state of the rock. Younger, hotter regions have thinner lithospheres, while older, cooler regions have developed thicker ones over time. The lithosphere behaves as a solid, breaking and fracturing when subjected to stress, and it is within this layer that earthquakes occur and tectonic plates are defined. When stress builds beyond the strength of the rock, the lithosphere fails suddenly, snapping along fault lines and releasing the accumulated strain energy as seismic waves that radiate outward through the Earth. Beneath the lithosphere lies a region called the asthenosphere, extending from roughly 100 kilometers down to about 250 to 350 kilometers below the surface. Though like many boundaries in Earth's interior, this transition occurs gradually rather than sharply. In this zone, the rock remains solid in composition but takes on a ductile plastic character. The asthenosphere flows and deforms over time, its semi-molten consistency allowing it to behave almost like thick honey or warm taffy when subjected to stress over long periods. This layer is primarily composed of a rock called peridotite, rich in olivine minerals that give it a distinctive greenish color when seen in the rare surface exposures of mantle rock. Despite being solid, the intense heat and pressure cause a small percentage of partial melting, perhaps 1 to 10% of the rock by volume, that gives the asthenosphere its distinctive flowing nature. This partial melt exists as thin films between solid mineral grains, lubricating their movement and allowing the rock as a whole to deform without breaking. The boundary between the lithosphere and asthenosphere, known scientifically as the LAB, or lithosphere-asthenosphere boundary, varies in depth from place to place depending on local conditions of temperature, pressure, and composition. This boundary represents a fundamental transition in the behavior of Earth's materials, a shift from rigid brittleness above to slow-flowing plasticity below. Scientists identify this boundary using seismic waves which travel at different speeds through the rigid lithosphere and the more plastic asthenosphere. The seismic wave velocities drop notably when waves pass from the lithosphere into the asthenosphere, a phenomenon that allows geophysicists to map the depth of this invisible boundary far beneath the surface. It is this boundary and the contrast between these two layers that enables one of the most important geological processes on our planet: plate tectonics. Deeper still, the mantle continues downward through what scientists call the transition zone, spanning from about 410 kilometers down to about 660 kilometers depth. In this region, rocks transform into denser crystal structures under increasing pressure. The mineral olivine, dominant in the upper mantle, transforms first into a structure called wadsleyite, and then into an even denser structure called ringwoodite as pressure increases with depth. These phase transitions occur at specific depths and cause sharp changes in seismic wave velocities that geophysicists can detect, allowing them to map the internal structure of the mantle despite never having directly sampled these depths. Below the transition zone lies the lower mantle, extending from about 660 kilometers down to the core mantle boundary at 2,890 kilometers depth. In the lower mantle, the immense pressure causes the mantle minerals to adopt an even more compact crystal structure called bridgmanite, and the rock becomes more rigid again despite the extremely high temperatures, because the enormous pressures override the weakening effect of heat. The temperature in the lower mantle reaches approximately 3,700 degrees Celsius near its base, hot enough to melt rock instantly at the surface but held solid here by the weight of all the material above pressing down with incomprehensible force. The pressure at the bottom of the mantle exceeds 1,300,000 times the atmospheric pressure at Earth's surface, a force so great that it fundamentally changes how atoms bond together and how materials behave. At the center of our world lies the core, beginning approximately 2,890 kilometers below the surface. The core itself has two parts: an outer core of liquid iron and nickel, swirling and circulating in currents that generate Earth's magnetic field through a process called the geodynamo, and an inner core of solid iron, kept in a solid state despite temperatures exceeding 5,000 degrees Celsius. Because the pressure at this depth is so extreme that atoms cannot move apart even at these fantastic temperatures. The inner core, approximately 2,400 kilometers in diameter, grows slowly as iron crystallizes out of the liquid outer core, releasing heat that helps drive the convection in the outer core above it. This layered structure of our planet exists as it does because of a process that occurred early in Earth's history, sometimes called the Iron Catastrophe. When the Earth was young and still molten from the heat of its formation, gravity pulled the heaviest elements toward the center while lighter materials rose toward the surface. Dense iron and nickel sank to form the core, while lighter silicate rocks formed the mantle, and the lightest minerals rose to form the crust. This natural sorting by density, called differentiation, created the layered structure that persists today and established the basic framework within which all geological processes operate. The engine that drives geological activity, including volcanoes and earthquakes, is heat. Earth contains a tremendous amount of thermal energy, some left over from the planet's violent formation billions of years ago, and some continuously generated by the radioactive decay of elements like uranium, thorium, and potassium deep within the mantle and crust. Estimates suggest that roughly half of the heat flowing out of Earth comes from primordial heat left over from the planet's formation, while the other half comes from ongoing radioactive decay. This heat must somehow escape to space, and it does so through a combination of processes, with convection being the dominant mechanism in the mantle, supplemented by conduction through the lithosphere and ultimately radiation from the surface into space. Convection in the Earth's mantle operates on the same basic principle as boiling water in a pot, though infinitely more slowly and far more complex in its details. Hot material, being less dense than cold material, rises upward through the mantle. As it rises, it gradually cools, and eventually this cooled material, now denser, begins to sink back down. These rising and sinking currents form what scientists call convection cells, vast circular patterns of flow that churn through the mantle over millions of years, transporting heat from the deep interior toward the surface. The mechanism of mantle convection is complex and still not completely understood in all its details, representing one of the active frontiers of geophysical research. Heat generated deep in the Earth, particularly at the boundary between the core and mantle, where heat flows from the even hotter core into the base of the mantle, warms the rock of the lower mantle. This heated rock expands slightly, becoming less dense than the cooler rock around it. The temperature difference and density contrast create buoyancy, causing the warmer rock to begin rising, though this rise occurs at speeds measured in centimeters per year rather than the rapid rise of bubbles in boiling water. The viscosity of the mantle rock, roughly 100,000 billion times more viscous than water, resists this motion, creating a drag force that slows the convective flow. But the thermal buoyancy persistently drives the circulation forward with patient, unstoppable force. As hot mantle material rises toward the surface, it eventually encounters the base of the lithosphere, the rigid outer shell that cannot participate in the flowing convection below. The rising material spreads horizontally beneath the lithosphere, rather like water spreading outward when it strikes the underside of a floating ice sheet, transferring heat through the thin thermal boundary layers where the flowing mantle meets the stationary lithosphere. In these boundary layers, typically only a few tens of kilometers thick, heat is transported through conduction rather than convection. Conduction occurs as vibrating atoms transfer energy to their neighbors without the material itself moving. And while conduction is generally slower than convection for heat transport because these boundary layers are thin, the temperature gradient is steep and the conductive heat transfer can be quite efficient. After spreading horizontally and losing heat to the lithosphere above, the mantle material cools and becomes denser. The cooling causes the rock to contract slightly and increases its density. Eventually, having given up much of its heat, this cooled material begins to sink back down into the depths of the mantle, completing the convective cycle. The descending material often takes the form of subducted oceanic lithosphere, cold slabs of surface rock that have been pushed down into the mantle at convergent plate boundaries. These sinking slabs are denser than the surrounding mantle, both because they are cooler and because oceanic lithosphere is compositionally denser than the asthenosphere. The slabs sink through the mantle, some penetrating all the way to the core mantle boundary, where they pile up and may eventually be reheated to begin the cycle again. The heat flow through the Earth from the interior to the surface is driven by this continuous patient circulation of solid rock flowing like a fluid over geological time. The rigid lithosphere sitting atop this slowly churning asthenosphere is not a single unbroken shell. Instead, the lithosphere is fractured into several large pieces and many smaller ones, rather like a cracked eggshell whose pieces remain fitted together but can move independently. These pieces are called tectonic plates, and they include both oceanic and continental crust along with the uppermost mantle rock that forms the lower part of the lithosphere. The flowing convection currents in the asthenosphere below exert drag forces on the bases of these plates, slowly pushing and pulling them across the surface of the Earth. Additionally, other forces act on the plates themselves. The weight of cold, dense subducting slabs pulls on the edges of plates. Gravity causes elevated mid-ocean ridges to push plates apart, and resistance at plate boundaries where plates collide or grind past each other resists motion. Currently, Earth's lithosphere is divided into 7 or 8 major tectonic plates, depending on how they are classified, along with many more minor plates. The major plates include the Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, sometimes divided into separate Indian and Australian plates, and the South American Plate. These plates move at various speeds driven by the convection currents below them and by forces generated at their edges. The rates of movement are exceedingly slow by human standards, but remarkably fast on geological timescales. The slowest moving plates, such as those near the Arctic Ridge, creep along at less than 2.5 centimeters per year, about the rate at which fingernails grow. Other plates move considerably faster. The Nazca Plate, which lies off the western coast of South America in the eastern Pacific Ocean, races along at about 16 centimeters per year, comparable to the rate at which human hair grows, making it one of the fastest moving plates on Earth. The Pacific Plate moves at intermediate speeds, traveling faster than the plates of the Atlantic Basin. Scientists have discovered that plates attached to subducting margins where one plate dives beneath another back into the mantle tend to move much faster than plates that are not subducting. The Pacific Plate, essentially surrounded by subduction zones in a ring called the Ring of Fire, moves notably faster than the Atlantic Plates, which are welded to the continents on either side of the Atlantic Ocean, and lack significant subduction zones along their edges. The pull of the dense sinking slabs at subduction zones appears to be one of the most powerful forces driving plate motion, literally dragging the plates along as the slabs sink into the mantle. Over hundreds of millions of years, these slow but persistent movements accumulate, causing continents to drift thousands of kilometers across the face of the Earth. The theory of continental drift, first seriously proposed by Alfred Wegener in the early 20th century and later incorporated into the broader framework of plate tectonics in the 1960s, explains how the continents we see today were once joined together and have since separated. Wegener noticed that the coastlines of Africa and South America seemed to fit together like pieces of a jigsaw puzzle, and that similar fossils and rock formations appeared on both continents, suggesting they were once connected, though initially dismissed by many scientists who could not imagine a mechanism powerful enough to move continents. His ideas were eventually vindicated when the mechanisms of mantle convection and seafloor spreading were discovered. The most recent supercontinent, called Pangaea, existed approximately 300 million years ago during the late Paleozoic and early Mesozoic eras. In Pangaea, all of Earth's major land masses were connected in a single giant continent surrounded by a vast ocean called Panthalassa. This supercontinent was not stable or permanent. The same convection forces that had brought the continents together continued to work beneath them, and eventually Pangaea began to break apart as rising mantle currents beneath it created zones of extension and rifting. The breakup of Pangaea occurred in several major phases spread across many tens of millions of years. The first phase began about 200 million years ago during the early Jurassic period, when Pangaea split into two large pieces. Laurasia in the north, which included what would become North America, Europe, and Asia, and Gondwana in the south, comprising future South America, Africa, Antarctica, Australia, and India. A narrow seaway called the Tethys Ocean opened between these two supercontinents, gradually widening as they drifted apart. The initial rifting created volcanic activity and earthquake sequences as the continent fractured. Processes similar to what we observe today in the East African Rift, where Africa is slowly beginning to split apart. The second major phase occurred between 150 and 140 million years ago during the early Cretaceous period, when Gondwana itself began to fragment. Africa separated from South America as the South Atlantic Ocean opened between them, driven by a mid-ocean ridge system that continues to produce new seafloor today. India broke away from Antarctica and Australia, and began a long journey northward toward its eventual collision with Asia. Australia remained connected to Antarctica for a time but would eventually separate. These processes of separation occurred gradually, driven by the persistent forces of mantle convection opening rifts in the continental crust and creating new oceanic crust between the diverging fragments. The final major phase of Pangaea's breakup unfolded during the early Cenozoic era, between approximately 60 and 50 million years ago. During this time, Laurasia split apart as Greenland and North America separated from Europe, opening the Norwegian Sea and expanding the northern Atlantic Ocean. Australia finally separated from Antarctica and began drifting northward toward its current position. India, having crossed what was once the Tethys Ocean, collided with the southern edge of Asia, a collision that created the Himalayan mountain range and continues to push those mountains higher today. As India continues pressing northward, converging at about 5 centimeters per year. Today, the continents continue their slow migration across the globe. GPS measurements, accurate to within millimeters, confirm that the plates are still moving at the rates measured by geological methods over millions of years. North America and Europe drift apart by about 2 to 3 centimeters per year as the Atlantic Ocean widens and new oceanic crust forms at the mid-Atlantic ridge. India continues pushing into Asia at about 5 centimeters per year, sustaining the growth of the Himalayas and causing frequent earthquakes in the region. Australia migrates northward at about 7 centimeters per year, slowly closing the distance between it and Southeast Asia. These movements seem imperceptibly slow on human timescales, but over millions of years they reshape the entire surface of the planet, closing oceans and opening new ones, assembling supercontinents and breaking them apart in a grand cycle that has repeated several times in Earth's history. The boundaries between tectonic plates are where geological activity concentrates, like the seams in a garment where stress tends to accumulate. 3 main types of plate boundaries exist, each characterized by different movements and different geological consequences. At divergent boundaries, plates move apart from each other, creating gaps that are filled by upwelling mantle rock that melts and forms new crust. At convergent boundaries, plates move toward each other, with one plate typically sliding beneath the other or both plates crumpling together. At transform boundaries, plates slide horizontally past each other, grinding along vertical or near vertical fault zones. Each type of boundary generates its own characteristic pattern of earthquakes and, in some cases, volcanic activity, creating the distribution of geological hazards we observe across the planet. It is at these plate boundaries and occasionally at weak points within plates that the slow accumulation of stress from plate movements is suddenly released in earthquakes. It is also at certain types of plate boundaries and at volcanic hotspots within plates where unusually hot mantle rises from great depths that molten rock from the mantle can reach the surface to create volcanoes. Understanding this framework of Earth's internal structure, the convection that drives plate motion, and the plate boundaries where that motion generates geological activity provides the foundation for understanding the specific mechanisms of volcanoes and earthquakes themselves. The story of our dynamic Earth is one of infinite patience and relentless change. Rock flows like honey when given enough time and subjected to enough pressure and heat. Continents drift like rafts on a slow-moving sea of stone. Mountains rise grain by grain, millimeter by millimeter, pushed upward by the collision of tectonic plates. Oceans open along rifts in the seafloor, widening by centimeters each year for millions upon millions of years until they span thousands of kilometers. In the gentle darkness of sleep, we can contemplate this vast, slow dance of the planet beneath us, appreciating the grand timescales on which Earth operates and the elegant processes that have shaped the world we inhabit. Beneath every step we take, beneath every building and every ocean, the planet continues its patient work, reshaping itself in ways that will only become apparent to generations far in the future. Understanding volcanoes. Mountains born of fire. A volcano is, in its essence, an opening in Earth's crust through which molten rock, gases, and other materials escape from the interior to the surface. The word volcano comes from Vulcan, the Roman god of fire, and while the name evokes images of dramatic eruptions and flowing lava, the reality of volcanoes encompasses a far broader and more nuanced range of phenomena. Some volcanoes erupt explosively, sending ash and rock fragments high into the atmosphere. Others erupt gently, with lava flowing quietly from vents and spreading across the landscape like thick syrup. Some volcanoes rise as towering peaks that dominate the horizon, while others form low, broad domes or exist as barely visible cracks in the ocean floor. All share a common origin in the movement of molten rock from depth toward the surface, driven by forces we explored in our journey through Earth's interior. Beneath every volcano lies a source of molten or partially molten rock called magma. This magma forms when rock in Earth's mantle or lower crust melts, a process that requires specific conditions of temperature, pressure, and composition. Rock does not simply melt because it gets hot. At the depths where magma forms, the pressure is so intense that it actually raises the melting point of rock far above what it would be at the surface. For rock to melt at these depths, something must change. Either the temperature must increase beyond the elevated melting point, or the pressure must decrease, lowering the melting point until it falls below the ambient temperature. Alternatively, adding water or other volatiles to the rock can dramatically lower its melting point, allowing it to melt even at temperatures that would normally keep it solid. Volcanoes form through three primary mechanisms, each associated with different tectonic settings and each producing magma through different processes. These three settings are subduction zones, where one tectonic plate dives beneath another, divergent boundaries where plates pull apart, and hotspots where unusually hot mantle material rises from great depths beneath a tectonic plate. Each setting creates its own characteristic type of volcano with distinctive eruption styles and hazards. At subduction zones, oceanic lithosphere that has grown old and cold during its journey away from mid-ocean ridges eventually encounters a convergent plate boundary. The oceanic plate, denser than the continental plate or younger oceanic plate it meets, begins to descend back into the mantle. As the subducting plate sinks deeper, it carries with it sediments from the ocean floor and water trapped in its minerals. The increasing temperature as the plate descends causes minerals to break down and release this water. The released water rises into the overlying mantle wedge, the region of mantle trapped between the subducting plate below and the overriding plate above. When water enters hot mantle rock, it acts as a flux, dramatically lowering the melting point of the minerals. Mantle rock that was stable as a solid suddenly begins to melt, generating magma rich in volatiles and various dissolved gases. This magma, being less dense than the solid rock around it, rises buoyantly through the overlying mantle and crust. The rise occurs slowly, the magma working its way upward through cracks and zones of weakness, sometimes pooling in chambers where it may reside for thousands of years before finally reaching the surface. When subduction zone magma does reach the surface, it often erupts explosively because of its high gas content. The dissolved gases, primarily water vapor and carbon dioxide, expand violently as pressure decreases near the surface, fragmenting the magma into ash and pyroclastic material. The volcanoes that form above subduction zones tend to be steep-sided stratovolcanoes, built up layer by layer from alternating deposits of lava flows and explosive debris. The Pacific Ring of Fire, a roughly 40,000-kilometer arc encircling the Pacific Ocean, contains the majority of Earth's subduction zone volcanoes. Here, oceanic plates around the Pacific Basin subduct beneath the surrounding continental and oceanic plates, creating volcanic arcs along the coasts of South America, Central America, North America, the Aleutian Islands, Kamchatka, Japan, the Philippines, Indonesia, New Zealand, and many other locations. The volcanoes of the Andes, the Cascades, and the islands of Japan and Indonesia all owe their existence to subduction, to the patient descent of cold oceanic lithosphere carrying water into the depths and triggering melting in the mantle above. At divergent boundaries, tectonic plates pull apart from each other, creating a gap that must be filled. As the plates separate, the pressure on the underlying mantle decreases. This pressure release, called decompression melting, allows the hot mantle rock to begin melting even though its temperature has not changed. The mantle beneath divergent boundaries is already hot, close to its melting point but held solid by the pressure of the overlying rock. When that pressure decreases as the plates separate, the melting point drops below the ambient temperature and the mantle begins to melt. The magma generated at divergent boundaries is typically basaltic, derived directly from partial melting of the mantle without significant modification by interaction with crustal rocks. This basaltic magma has relatively low viscosity and low gas content compared to subduction zone magmas, causing it to erupt more gently. At mid-ocean ridges, the divergent boundaries that run through all the major ocean basins, this basaltic magma rises and erupts along the ridge axis, creating new oceanic crust. Most of this volcanism occurs underwater and goes unobserved by humans, but it is remarkably productive. The mid-ocean ridge system generates approximately 20 square kilometers of new oceanic crust every year, making it by far the most volcanically active environment on Earth, though its activity occurs mostly hidden beneath kilometers of ocean water. In some locations, divergent boundaries occur within continents rather than beneath oceans. The East African Rift System represents an example of continental rifting, where the African continent is slowly being pulled apart. Here, the volcanism differs somewhat from mid-ocean ridges because the magma must rise through thick continental crust rather than thin oceanic crust. As the magma interacts with continental rocks, it may assimilate some of that material, changing its composition and making eruptions somewhat more explosive than typical mid-ocean ridge volcanism. Nevertheless, the fundamental process remains decompression melting of the mantle as the rift pulls apart. Iceland sits directly atop the mid-Atlantic ridge, one of the few places where a divergent plate boundary rises above sea level. Here, we can observe directly the processes that normally occur hidden beneath the ocean. Volcanic eruptions in Iceland produce extensive lava flows that spread across the landscape, building the island gradually higher and wider. The volcanic activity is frequent but generally not catastrophically explosive, though exceptions occur when magma encounters groundwater, producing violent steam-driven eruptions. The third major setting for volcano formation involves hotspots, localized regions of unusually hot mantle that rise as plumes from deep within Earth's interior. The exact depths from which hotspot plumes originate remains debated among geologists. but evidence suggests many rise from the core mantle boundary nearly 3,000 kilometers below the surface. At this boundary, the immense heat flowing from the outer core into the base of the mantle creates thermal instabilities. Occasionally, a mass of abnormally hot mantle begins to rise, its buoyancy driven by its lower density compared to surrounding mantle. These mantle plumes rise slowly through the mantle, taking millions of years to ascend from the core mantle boundary to the base of the lithosphere. When a plume head reaches the lithosphere, its heat causes extensive melting, generating large volumes of magma. Unlike subduction zones and divergent boundaries, hotspots are not directly associated with plate boundaries. Instead, they occur within plates, creating volcanoes in the middle of oceanic plates or continental interiors far from any plate edge. The Hawaiian Islands provide the classic example of hotspot volcanism. The Hawaiian hotspot has remained relatively stationary deep in the mantle while the Pacific plate moves across it, like a piece of paper sliding over a blowtorch. As the plate moves, the hotspot burns through it, creating a volcano. That volcano erupts and grows, building an island over hundreds of thousands of years. Eventually, however, plate motion carries the volcano away from the hotspot, cutting off its magma supply. Volcanic activity ceases and the island begins to erode. Meanwhile, the hotspot continues burning through the plate in its new location, creating a new volcano and a new island. This process, repeated over millions of years, creates a chain of islands stretching across the ocean, with the oldest, most eroded islands at one end, and the youngest, most volcanically active island at the other. The Hawaiian island chain stretches for approximately 2,400 kilometers across the Pacific, with the big island of Hawaii at the southeastern end still positioned over the hotspot and actively erupting, while the northwestern islands grow progressively older and more eroded. Hotspot volcanoes tend to produce fluid basaltic lava that erupts relatively gently. The Hawaiian volcanoes are shield volcanoes, so named because their broad, gentle slopes resemble a warrior's shield laid flat on the ground. These volcanoes grow through countless eruptions, each adding a new layer of lava that spreads widely before solidifying. Over time, the accumulated layers build a massive mountain, though the slopes remain gentle because each individual lava flow spreads so widely before freezing. Yellowstone represents a continental hotspot, where a mantle plume rises beneath the North American plate. The Yellowstone hotspot differs from Hawaii in that the magma must rise through thick continental crust, and interaction with this crust changes the magma composition, making it more viscous and gas-rich. Yellowstone has a history of extraordinarily explosive eruptions, the most recent major one occurring approximately 640,000 years ago. These eruptions were so voluminous that the ground collapsed into the emptied magma chamber, creating a giant caldera, a volcanic crater tens of kilometers across. Today, Yellowstone remains volcanically active, though it has not erupted explosively for hundreds of thousands of years. The heat from the magma chamber below drives the famous geysers and hot springs that make Yellowstone a spectacular natural laboratory for studying volcanic processes. All three volcano formation mechanisms ultimately depend on melting rock and transporting that melt from depth to surface. The magma generated in each setting rises because it is less dense than the surrounding solid rock. A cubic meter of solid basalt weighs approximately 3,000 kilograms, while the same volume of molten basalt weighs only about 2,700 kilograms. This density difference creates powerful buoyancy forces that drive magma upward through cracks and conduits in the overlying rock. As magma rises, it may ascend directly to the surface, or it may accumulate in magma chambers, regions where the magma pools and resides for periods ranging from years to hundreds of thousands of years. Magma chambers form at depths where the magma's buoyancy balances the resistance of the overlying rock, often at boundaries between different rock types, or where the crust's strength prevents further upward progress. These chambers are not empty caverns filled with liquid rock, but rather complex systems of partially molten mush, where liquid magma permeates a crystal-rich matrix. Within a magma chamber, various processes modify the magma's composition and properties. Crystals form and settle, removing certain elements from the liquid and concentrating others. Magmas of different compositions may mix. The magma may assimilate pieces of the surrounding rock, incorporating new chemical components. Gases dissolved in the magma may separate and accumulate in the upper parts of the chamber. All these processes affect what will eventually erupt at the surface. The time magma spends in chambers allows heat to conduct into the surrounding rock, sometimes metamorphosing it or partially melting it. The gradual accumulation of magma causes the ground surface above to inflate slowly, sometimes rising centimeters per year as the chamber fills. This inflation can be measured using precise GPS instruments and satellite radar, providing volcanologists with a way to monitor magma movement beneath active volcanoes, even when they are not erupting. When pressure in a magma chamber exceeds the strength of the overlying rock, or when new magma enters from below and compresses the chamber contents, an eruption may begin. Magma forces its way through the weakest path available, often following existing fractures or creating new ones. As the magma approaches the surface, pressure decreases and dissolved gases begin to exsolve, forming bubbles. If the magma is fluid and gas can escape easily, lava flows gently from vents. If the magma is viscous and traps gases, pressure builds until the magma fragments explosively, creating pyroclastic eruptions that scatter ash across vast areas. The diversity of volcanic phenomena reflects the diversity of conditions under which magma forms and erupts. Subduction zones produce volatile, rich, explosive volcanoes. Divergent boundaries generate gentle, effusive eruptions that create new crust. Hotspots burn through plates, creating island chains or continental flood basalts. Yet all share the same fundamental story. Rock melts at depth, rises through buoyancy, and finds pathways to the surface where it emerges as lava, ash, or gas. Understanding this process from the initial melting deep in the mantle to the final eruption at the surface allows us to appreciate volcanoes not as random catastrophes, but as natural expressions of Earth's internal heat escaping to the surface, part of the planet's patient work of cooling itself over geological time. The gentle architecture of volcanic systems. The internal structure of a volcano resembles a complex plumbing system, with pathways and chambers connecting the deep sources of magma to the surface vents where eruptions occur. Understanding this architecture helps us appreciate how volcanoes function as conduits for Earth's internal heat, each component playing a role in the journey of molten rock from depth to daylight. At the deepest level lies the source region where magma first forms. In subduction zones, this occurs in the mantle wedge above the descending plate, typically at depths between 70 and 200 kilometers below the surface. At divergent boundaries, melting occurs in the uppermost mantle directly beneath the rift, at depths of perhaps 10 to 30 kilometers. At hotspots, the source region may extend down to the core mantle boundary, though most melting occurs when the rising plume reaches the shallow mantle beneath the lithosphere. This source region is not a discrete chamber, but rather a broad zone where temperature, pressure, and composition combine to cause partial melting of the rock. From the source region, magma begins its ascent. The initial rise occurs through a process called porous flow, where liquid magma percolates upward through tiny spaces between solid mineral grains, rather like water seeping through sand. As magma accumulates, it eventually forms larger bodies that can generate enough pressure to fracture the overlying rock, creating pathways called dikes. These dikes are vertical or near-vertical sheets of magma that intrude through the surrounding rock, exploiting zones of weakness and creating new fractures as they propagate upward. The magma's ascent is not continuous or rapid. It rises in fits and starts, sometimes stalling at certain depths where its buoyancy cannot overcome the resistance of the overlying rock. At these depths, magma may accumulate in reservoirs or chambers, regions where the magma pools and resides, sometimes for thousands of years. These chambers occupy zones where the rock above is particularly strong or where the magma encounters boundaries between different rock types with contrasting mechanical properties. A magma chamber is not a hollow cavern filled with liquid rock, as popular imagination might suggest. Instead, it consists of a complex mixture of liquid melt, solid crystals that have formed as the magma slowly cools, and gases that have exhaled from the liquid. The proportions of these components vary throughout the chamber and change over time. Near the roof of the chamber, where temperatures are coolest, the proportion of crystals may exceed 50%, creating a crystal-rich mush. In the center and lower portions, where temperatures remain higher, the magma may be more liquid, though even here crystals float and slowly settle according to their density. The size of magma chambers varies enormously. Small volcanic systems may have chambers containing just a few cubic kilometers of magma, while the largest systems, like Yellowstone, contain chambers with volumes of thousands of cubic kilometers. These massive chambers develop over hundreds of thousands of years through repeated injections of fresh magma from below. Each new injection adds heat and material, preventing the chamber from freezing solid and maintaining the partially molten state necessary for future eruptions. Above the main magma chamber, smaller secondary chambers or dikes may form at shallower depths. These smaller reservoirs act as staging areas where magma pauses during its final approach to the surface. The pressure and stress fields around these shallow magma bodies cause the overlying rock to fracture in characteristic patterns. Some fractures radiate outward from the magma body like spokes from a wheel hub, while others form concentric rings around it. When magma intrudes into these fractures, it creates networks of dikes and sills that surround the main conduit system. The final segment of a volcano's plumbing is the conduit, the pipe or channel through which magma travels from the uppermost chamber to the surface vent. In some volcanoes, the conduit is a relatively simple cylindrical pipe, perhaps tens to hundreds of meters in diameter, lined with solidified magma from previous eruptions. In others, the conduit may be more complex, branching into multiple pathways that feed different vents or fissures at the surface. The conduit's diameter influences eruption style. Narrow conduits restrict the flow of magma and may contribute to explosive eruptions by increasing friction and allowing pressure to build. Wider conduits allow easier magma ascent and tend to favor effusive eruptions with flowing lava. At the surface, the conduit opens at a vent, the actual opening through which material erupts. A single volcano may have multiple vents, sometimes located on the flanks of the mountain rather than at the summit. These flank vents form when magma finds an easier path to the surface through the side of the volcanic edifice rather than rising all the way to the central vent. Over time, eruptions from multiple vents build a complex volcanic structure, with lava flows and pyroclastic deposits overlapping from different source points. Surrounding the main edifice, volcanoes often feature additional structural elements. A crater may exist at the summit, a depression formed by explosive eruption or by collapse of the summit into a shallow magma chamber. If a very large volume of magma erupts rapidly, the chamber may empty partially or completely, and the unsupported roof collapses into the void, creating a much larger depression called a caldera. Calderas can span many kilometers in diameter, and may themselves become the sites of new volcanic vents as magma accumulates again in the chamber below. The shape and structure of a volcano reflect its eruption history and the type of material it has erupted. Shield volcanoes, like those in Hawaii, have gentle slopes typically between 2 and 10 degrees. This gentle profile results from the eruption of fluid basaltic lava that flows easily and spreads widely before solidifying. Each eruption adds a thin layer of lava to the edifice, and countless such layers accumulated over hundreds of thousands of years build a broad, dome-shaped mountain. The largest shield volcanoes, like Mauna Loa in Hawaii, are among the most massive mountains on Earth. Mauna Loa rises approximately 4,170 meters above sea level, but its base sits on the ocean floor 5,000 meters below sea level, giving it a total height of over 9,000 meters from base to summit, taller than Mount Everest when measured this way. Stratovolcanoes, also called composite volcanoes, have much steeper slopes, typically between 30 and 40 degrees near the summit. These volcanoes form from alternating layers of lava flows and pyroclastic material, the products of both effusive and explosive eruptions. The pyroclastic layers consist of ash, pumice, and rock fragments ejected during explosive events, while lava flows are extruded during quieter phases of activity. The alternation of these different materials creates the layered structure that gives stratovolcanoes their name. Mount Fuji in Japan, Mount Rainier in Washington, and Mount Vesuvius in Italy are all stratovolcanoes, their steep, symmetric cones instantly recognizable as the archetypal volcanic form. Cinder cones are smaller, simpler volcanoes formed entirely from pyroclastic material. These form when gas-rich magma erupts explosively, fragmenting into small pieces that arc through the air and land around the vent. The fragments pile up into a cone-shaped hill with steep sides, typically between 30 and 40 degrees, which is approximately the angle of repose for loose granular material. Cinder cones are usually monogenetic, meaning they form during a single eruptive episode and then become extinct. They rarely exceed a few hundred meters in height and may form as parasitic cones on the flanks of larger volcanoes. Lava domes form when highly viscous lava extrudes slowly from a vent, piling up around the opening rather than flowing away. The lava is so thick and sticky that it cannot flow far before solidifying. Instead, it accumulates as a steep-sided dome or plug, often with an irregular, lumpy surface. The dome grows through internal expansion as new lava pushes up from below rather than through surface flows. Lava domes can be dangerous because their steep sides and unstable structure make them prone to collapse, generating pyroclastic flows that race down the volcano's flanks. The volcanic edifice itself is just the visible portion of a much larger volcanic system that extends deep into the crust and upper mantle. For every cubic kilometer of rock visible at the surface, many more cubic kilometers of intrusive igneous rock exist at depth, frozen magma that never reached the surface but instead solidified within the crust. These intrusive rocks form the deep roots of volcanic systems, and they may only become visible millions of years later if erosion removes the overlying rock. Around active volcanoes, the ground may be fractured by faults and fissures related to the volcanic plumbing. The pressure exerted by rising magma and the inflation of magma chambers cause the overlying rock to stretch and fracture. These fractures create pathways for volcanic gases to escape even when the volcano is not erupting. Fumaroles, vents that emit steam and other gases, dot the flanks of many volcanoes, releasing gases that percolate upward from the magma chamber or from groundwater heated by the volcanic system. The gases include water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide, creating distinctive and sometimes pungent odors around volcanic areas. Hot springs often occur near volcanoes where groundwater circulates through hot rock, absorbing heat before emerging at the surface. The water may emerge gently as warm springs, or it may erupt periodically as geysers if the underground plumbing creates the right conditions for pressure to build and release rhythmically. These geothermal features reveal the presence of heat at depth and demonstrate that volcanic systems remain thermally active even between eruptions. The architecture of volcanic systems evolves over time. Young volcanoes may have simple structures with a single conduit feeding a single vent. As they mature and experience many eruptions, their plumbing becomes more complex. Multiple chambers may develop at different depths. Networks of dikes intrude through the edifice. Flank vents open and feed parasitic cones. The summit may collapse to form a caldera, which then becomes the site of renewed volcanic activity. Ancient volcanoes that have ceased erupting may be deeply eroded, exposing their internal structure and revealing the frozen magma conduits and chambers that once fed eruptions. Understanding volcanic architecture helps scientists monitor active volcanoes and assess hazards. Changes in the volcanic plumbing manifest as measurable signals at the surface. The ground inflates when magma enters chambers and deflates when magma drains out during eruptions. Earthquakes occur as rising magma fractures rock and as existing fractures adjust to changing stress. Gas emissions increase when new magma brings fresh volatiles into the system. By monitoring these signals, volcanologists can glimpse the hidden movements occurring in the volcanic plumbing deep below and sometimes anticipate eruptions before they occur. The patient construction of volcanic edifices layer by layer through countless eruptions over hundreds of thousands of years reminds us of the immense timescales on which geological processes operate. Each lava flow, each ash deposit, each intrusive dike represents a moment in the volcano's life frozen in stone. The accumulation of these moments builds mountains, reshapes landscapes, and continues the endless work of moving heat from Earth's interior to its surface. Eruption types, from quiet flows to dramatic displays. Volcanic eruptions occur in a remarkable variety of styles, from gentle effusions of lava that flow like slow-moving rivers to catastrophic explosions that hurl ash and rock tens of kilometers into the atmosphere. These different eruption styles reflect variations in magma composition, gas content, viscosity, and the pathways through which the magma reaches the surface. Understanding these eruption types helps us appreciate the diverse ways Earth releases its internal heat and reshapes its surface. Volcanologists classify eruptions based on their behavior and intensity, often naming the categories after volcanoes that exemplify each style. This classification system recognizes that eruptions exist on a continuum rather than in discrete categories. But grouping them helps us understand the factors that control volcanic behavior and anticipate the hazards different volcanoes might pose. Hawaiian eruptions represent the gentlest end of the eruption spectrum. Named after the volcanoes of Hawaii, where this style is common, Hawaiian eruptions involve the effusion of very fluid basaltic lava with low gas content. The magma in these eruptions has been heated to high temperatures, typically between 1,100 and 1,200 degrees Celsius, giving it low viscosity comparable to motor oil or honey. When this fluid magma reaches the surface, dissolved gases escape relatively easily, bubbling out without building dangerous pressure. During a Hawaiian eruption, lava typically emerges from fissures or vents and flows downslope under the influence of gravity. The flows may travel at speeds of several kilometers per hour when first erupted on steep slopes, but they slow as they cool and as the slope decreases. Lava channels may form, confining the flow to a defined path and allowing it to travel many kilometers from the source. In some cases, the surface of the flow cools and solidifies while molten lava continues to flow beneath, forming lava tubes that insulate the liquid interior and allow the lava to travel even greater distances while remaining hot and fluid. Hawaiian eruptions can produce spectacular lava fountains when gas bubbles burst vigorously at the vent, throwing molten lava tens to hundreds of meters into the air. These fountains are not explosive in the dangerous sense, but rather represent vigorous bubble bursting, similar to champagne overflowing from a bottle but on a vastly larger scale. The lava droplets ejected by the fountains are usually still molten when they land, and they coalesce back into flows rather than forming solid fragments. The lava flows from Hawaiian eruptions typically have one of two surface textures. Pahoho lava has a smooth, ropey surface that forms when the cooling lava surface wrinkles as the molten interior continues to flow. The surface resembles coiled rope or braided fabric with smooth, billowy forms. Aa lava, in contrast, has a rough, jagged surface composed of sharp, angular fragments. A forms when lava flows more turbulently or cools more rapidly, causing the surface to break into clinkers that give the flow a chaotic, blocky appearance. Walking across Aa lava, even after it has completely solidified, is treacherous due to the sharp, unstable fragments that cover the surface. Hawaiian eruptions pose relatively limited hazards to human life because the lava flows move slowly enough that people can usually evacuate ahead of them. The primary danger is to property, as lava flows inexorably destroy everything in their path, burning buildings and burying infrastructure under meters of solidified rock. The eruptions can continue for months or even years, with lava flows gradually expanding to cover larger areas. Strombolian eruptions, named after the volcano Stromboli in Italy's Aeolian Islands, represent a step up in explosivity. Stromboli has been erupting almost continuously for thousands of years, producing regular bursts of incandescent lava fragments every few minutes to hours. This rhythmic activity has earned Stromboli the nickname Lighthouse of the Mediterranean, as sailors have long used its glow for navigation at night. In Strombolian eruptions, gas bubbles rise through magma in the upper conduit and burst at the surface with more vigor than in Hawaiian eruptions. Each burst ejects fountains of molten lava called scoria or cinders that arc through the air and land around the vent. The fragments are usually still molten or partially molten when they land, and they weld together or pile up to form a cone-shaped hill called a cinder cone or scoria cone around the vent. The regular rhythmic nature of Strombolian eruptions suggests a steady gas supply rising through the magma, with each gas slug bursting as it reaches the surface. Between the explosive bursts, lava may flow from vents at the base of the cone, producing small flows similar to those in Hawaiian eruptions. The alternation between explosive activity that builds the cone and effusive activity that produces flows is characteristic of Strombolian volcanism. The eruptions are more energetic than Hawaiian eruptions, but generally not dangerous to observers who maintain a safe distance, as the fragments typically land within a few hundred meters of the vent. Volcanian eruptions, named after the island of Volcano in Italy, are significantly more explosive. In these eruptions, thick, viscous magma plugs the volcanic conduit between eruptive events. Gas pressure builds beneath the plug until it becomes strong enough to shatter the plug explosively. The eruption begins with a violent explosion that pulverizes the plug and excavates some of the upper conduit, ejecting a dense cloud of ash and rock fragments. This initial explosion may be followed by a sustained eruption as pressurized magma beneath continues to escape. The eruption clouds from volcanian explosions rise several kilometers into the atmosphere, typically reaching heights of 5 to 15 kilometers. The clouds are dense and dark, laden with ash particles and rock fragments that fall back to Earth over a wide area downwind of the volcano. Individual volcanian explosions may last minutes to hours, and they may recur as new plugs form and are destroyed in turn. The ash and fragments ejected during volcanian eruptions consist partly of fresh magma, blown apart by expanding gases and partly of older rock from the conduit walls in previous eruptions. This mixture of juvenile volcanic material and older fragments, called tephra, blankets the landscape around the volcano, sometimes accumulating to depths of centimeters or meters. The fine ash can be carried by winds for hundreds of kilometers, affecting areas far from the volcano itself. Plinian eruptions represent the most violent and catastrophic eruption style, named after Pliny the Younger, who documented the eruption of Mount Vesuvius in 79 CE that destroyed Pompeii and Herculaneum. Plinian eruptions involved the sustained ejection of enormous volumes of gas and pyroclastic material into the stratosphere. The eruption column in a Plinian event can reach heights of 25 to 45 kilometers, penetrating well into the stratosphere where winds may carry the ash around the globe. In a Plinian eruption, highly gas-rich magma rises rapidly through the conduit. As it approaches the surface, the decreasing pressure causes dissolved gases to exsolve explosively, fragmenting the magma into fine ash and pumice. The mixture of hot gases and pyroclastic material, having a bulk density lower than the surrounding atmosphere, rises as a powerful convective column, drawing in air from the sides and accelerating upward. The column billows outward at the top as it reaches neutral buoyancy in the stratosphere, forming the characteristic mushroom or umbrella shape associated with the most powerful eruptions. The eruption column can sustain itself for hours or even days, continuously ejecting material. The volume of magma erupted in a Plinian event can reach cubic kilometers to tens of cubic kilometers. The ash and pumice fall from the eruption column across vast areas, accumulating in blankets that may be meters thick near the volcano and centimeters thick hundreds of kilometers away. The weight of this accumulating tephra can collapse roofs and bury entire communities. If the eruption rate becomes too high for the column to remain buoyant, or if the column loses strength and collapses, a different and even more dangerous phenomenon occurs. Pyroclastic flows. These are ground-hugging avalanches of hot gas, ash, and rock fragments that race down the volcano's slopes at speeds that can exceed 100 kilometers per hour. The temperature within a pyroclastic flow can exceed 700 degrees Celsius, instantly incinerating everything in its path. The flows are denser than air but flow almost like a fluid, following valleys and funneling through low points in the topography. They can travel tens of kilometers from the volcano, devastating an area far larger than the lava flows or falling tephra alone would affect. The 79 CE eruption of Vesuvius produced pyroclastic flows that buried Pompeii and Herculaneum under meters of hot ash and pumice, killing thousands of people who were unable to evacuate in time. The heat of the flows was so intense that it killed instantaneously, leaving bodies frozen in their final postures, later preserved as cavities in the solidified ash. Pliny the Younger's written account, composed from observations made from across the Bay of Naples, provides one of the first detailed descriptions of a major volcanic eruption in Western literature. Phreatomagmatic eruptions occur when magma interacts explosively with water. This can happen when magma rises through wet ground, encounters a lake or ocean, or intrudes into an aquifer. The water flashes to steam, expanding by a factor of roughly 1,600 times its liquid volume in a fraction of a second. This rapid expansion shatters the magma and excavates a crater, ejecting a mixture of steam, water, magma fragments, and country rock. These eruptions are particularly violent relative to the volume of magma involved because the energy driving the explosion comes from the water's rapid phase change rather than solely from volcanic gases dissolved in the magma. The explosion can excavate craters hundreds of meters deep and across, creating features called maars. The ash ejected during phreatomagmatic eruptions is often very fine, because the violence of the water-magma interaction pulverizes the material into tiny particles, Surtsean eruptions, named after the volcanic island of Surtsey that emerged off Iceland's coast in 1963, are a subset of phreatomagmatic eruptions that occur when submarine volcanic vents approach sea level. As the growing volcanic cone reaches shallow water, the interaction between magma and seawater becomes particularly explosive, throwing jets of ash and steam hundreds of meters into the air. The eruptions build the island above sea level through the accumulation of ash, which is then cemented by subsequent lava flows into solid rock. Surtsey grew from the seafloor to an island exceeding 150 meters in height over the course of several years of intermittent eruptions. Submarine eruptions occur when volcanoes erupt beneath significant depths of water, typically along mid-ocean ridges or at submarine seamounts. The high pressure exerted by the overlying water column suppresses explosive activity, causing the eruptions to be effusive even if the magma composition might produce explosive eruptions on land. Lava erupting underwater cools rapidly, and the outer surface solidifies quickly while the interior remains molten. This creates distinctive pillow lava, rounded blobs or tubes of basalt that pile up on the seafloor like stacked pillows. The water surrounding submarine eruptions cools the lava so efficiently that pillow lavas can form even from compositions that would produce fluid flows on land. The rapid cooling creates volcanic glass on the pillow surfaces, black or dark green material with a glassy luster. These submarine eruptions go largely unobserved by humans because they occur beneath kilometers of ocean water. Yet they are by far the most common type of volcanism on Earth, continuously creating new oceanic crust along the mid-ocean ridge system. The factors controlling eruption style include magma composition, gas content, viscosity, temperature, and eruption rate. Basaltic magma, with roughly 50% silica content, has low viscosity when hot, allowing gases to escape easily and favoring effusive eruptions. Andesitic magma with roughly 60% silica is more viscous, trapping gases more effectively and favoring more explosive eruptions. Rhyolitic magma with roughly 70% silica is extremely viscous, and eruptions of rhyolite tend to be highly explosive or, if gas poor, to form thick, slow-moving lava domes. Gas content is equally important. Magma with high dissolved water and carbon dioxide content will erupt more explosively than gas-poor magma of identical composition. The gases provide the energy for explosive eruptions by expanding as pressure decreases. Magma that has degassed during slow ascent or residence in a shallow chamber may erupt effusively, even if its composition would normally favor explosive behavior. Temperature affects viscosity dramatically. Hotter magma flows more easily than cooler magma of the same composition. A basalt at 1,200 degrees Celsius behaves as a fluid, but if it cools to 1,000 degrees Celsius, its viscosity increases significantly and it flows more sluggishly. The eruption rate, or the volume of magma erupted per unit time, influences whether an eruption column remains stable or collapses to form pyroclastic flows. Higher eruption rates feed taller, more powerful columns, but if the rate becomes too high, the column may become unstable and collapse under its own weight. Volcanic eruptions, despite their potential for destruction, are fundamentally creative processes. They build new land, enrich soils, release gases that have contributed to Earth's atmosphere and oceans over geological time, and transport heat and material from the deep interior to the surface. Each eruption style reflects a particular balance of physical and chemical conditions, a specific outcome of the interplay between the properties of molten rock, dissolved gases, and the pathways through which they escape. In the quiet darkness, we can reflect on these processes as expressions of Earth's ongoing evolution. Dramatic at times, but patient in the longer perspective, slowly reshaping the planet through countless eruptions over billions of years. The science of earthquakes. when the Earth adjusts. An earthquake is the shaking and vibration of Earth's surface caused by the sudden release of energy stored in rocks beneath the ground. While volcanic eruptions represent the ascent of material from depth, earthquakes represent the sudden adjustment of rock masses in response to accumulated stress. Both phenomena reflect Earth's dynamic nature, but earthquakes occur far more frequently and in a wider variety of settings than volcanic eruptions. Understanding earthquakes requires understanding how rocks store elastic energy and how they fail when that energy exceeds their strength. The lithosphere, Earth's rigid outer shell, is constantly subjected to forces from plate motion. Where plates converge, compressional forces push rocks together. Where plates diverge, extensional forces pull rocks apart. Where plates slide past each other horizontally, shear forces cause rocks to grind against one another. These forces do not cause immediate, continuous motion. Instead, friction along fault surfaces locks the rocks in place while stress accumulates gradually, year after year, decade after decade. The rocks respond to this stress by deforming elastically, much as a rubber band stretches when pulled. The deformation stores energy in the strained rock. As long as the friction holding the fault surfaces together exceeds the forces trying to move them, the rocks remain locked and the strain continues to accumulate. However, rock strength is finite. Eventually, the accumulated stress exceeds the frictional strength holding the fault locked, and the rocks suddenly slip past each other. This sudden motion releases the stored elastic energy as seismic waves that radiate outward through the earth, causing the ground to shake. After the earthquake, the rocks occupy new positions and the cycle of stress accumulation begins again. This process, called elastic rebound theory, was first clearly articulated after the great 1906 San Francisco earthquake. Geodetic surveys before and after the earthquake showed that the ground on opposite sides of the San Andreas Fault had moved horizontally by several meters during the earthquake. The evidence indicated that the rocks had been gradually bending and straining for decades or centuries before suddenly snapping back to a less strained configuration, like a bent stick that suddenly breaks and releases its stored energy. Earthquakes occur most frequently along plate boundaries where tectonic forces are strongest and most consistent. The boundaries between tectonic plates represent zones of accumulated stress where the motion of the plates generates continuous deformation. At convergent boundaries where plates collide, earthquakes occur both along the interface where one plate slides beneath another and within the subducting plate itself as it bends and descends into the mantle. At divergent boundaries, earthquakes occur as the plates pull apart and the crust fractures to accommodate the extension. At transform boundaries, earthquakes occur as the plates grind horizontally past each other along strike-slip faults. The San Andreas Fault in California exemplifies a transform plate boundary. Here, the Pacific Plate moves northwestward relative to the North American Plate at roughly 5 centimeters per year. This motion is not smooth and continuous. Instead, most of the fault is locked by friction most of the time, and the motion occurs in sudden jumps during earthquakes. The 1906 San Francisco earthquake released roughly 300 years of accumulated strain in less than a minute, with some portions of the fault slipping by up to 6 meters. Subduction zones generate the largest and most devastating earthquakes on Earth. Along these boundaries, oceanic lithosphere descends beneath another plate at rates of several centimeters per year. But friction locks the interface between the two plates. The overlying plate is dragged downward and compressed as the subducting plate descends. Stress accumulates over decades or centuries until the interface ruptures in a massive earthquake. The largest earthquake ever recorded by instruments, the 1960 Chilean earthquake, occurred at a subduction zone and had a magnitude of 9.5. The 2004 Indian Ocean earthquake, which generated the devastating tsunami, and the 2011 Tohoku earthquake that struck Japan were both subduction zone earthquakes exceeding magnitude 9. These giant earthquakes occur because subduction zone faults can accumulate enormous amounts of strain over hundreds of years, and because the fault surfaces are enormous, extending for hundreds of kilometers along the plate boundary and down to depths of 50 kilometers or more. The total energy released when such a large fault area slips several meters is correspondingly immense, equivalent to thousands of nuclear weapons. Earthquakes also occur within tectonic plates far from plate boundaries, though less frequently. These intraplate earthquakes result from ancient zones of weakness in the lithosphere or from stress transmitted through the plates from forces acting at their edges. The New Madrid earthquakes of 1811 and 1812, which struck the central United States near the Mississippi River, were powerful intraplate earthquakes that occurred in an ancient rift zone where the continent nearly split apart 600 million years ago. Though the rifting failed and the continent remained intact, the zone of weakness remained, and it occasionally generates earthquakes when stress accumulates sufficiently. The depth at which earthquakes occur varies depending on the tectonic setting and the temperature and pressure conditions. Most earthquakes occur in the upper 15 to 20 kilometers of the crust, where rocks are cool and brittle enough to fracture suddenly. Deeper in the crust, increasing temperature causes rocks to become more ductile, and they deform by flowing rather than breaking. However, in subduction zones, cold oceanic lithosphere descends into the mantle, carrying cool, brittle rock to great depths. Earthquakes can occur within this descending slab down to depths of roughly 700 kilometers, where the pressure finally becomes so great that even cold rock cannot fracture in the brittle fashion required for earthquakes. These deep earthquakes occur by different mechanisms than shallow earthquakes. At depths beyond about 300 kilometers, the pressure is too high for ordinary brittle fracture. Instead, earthquakes may result from sudden phase transitions in minerals, where the crystal structure of a mineral collapses to a denser form, releasing energy. Alternatively, they may result from dehydration reactions that release water from minerals, temporarily weakening the rock and allowing sudden slip. The exact mechanisms of deep earthquakes remain an active area of research, but their occurrence demonstrates that Earth's interior can release energy suddenly even under conditions where ordinary fracture cannot occur. When an earthquake occurs, the point within the Earth where the fault first ruptures is called the hypocenter or focus. The rupture does not happen instantaneously across the entire fault surface. Instead, it begins at the hypocenter and propagates outward along the fault, unzipping it at speeds of several kilometers per second. The total time it takes for the fault rupture to propagate depends on the fault's dimensions. Small earthquakes may rupture in a fraction of a second, while the largest earthquakes can take several minutes for the rupture to propagate across the entire fault surface. The point on Earth's surface directly above the hypocenter is called the epicenter. This is the location usually reported in earthquake announcements, as it is the surface location closest to the origin of the earthquake. The intensity of shaking is often greatest near the epicenter, though local geological conditions can cause strong shaking at greater distances if the seismic waves are amplified by soft sediments or focused by subsurface structures. Earthquakes range enormously in size and energy release. The smallest earthquakes detectable by sensitive seismometers have magnitudes below 0 and release energy equivalent to small firecrackers. These micro-earthquakes occur constantly around the world, with millions happening every day, though most are too small to be felt. At the other extreme, the largest earthquakes exceed magnitude 9 and release energy equivalent to thousands of nuclear weapons, approximately 32,000 times more energy than a magnitude 6 earthquake. The frequency of earthquakes decreases dramatically with increasing magnitude. For every magnitude 7 earthquake, roughly 10 magnitude 6 earthquakes occur, 100 magnitude 5 earthquakes, 1,000 magnitude 4 earthquakes, and so on. This relationship, called the Gutenberg-Richter law, reflects the fractal nature of faulting in Earth's crust, where faults of all sizes exist and where smaller faults are much more numerous than larger ones. Aftershocks follow most significant earthquakes, sometimes continuing for months or years. These are additional earthquakes triggered by the stress changes caused by the main shock. When a fault slips during an earthquake, it reduces stress on the fault that slipped but increases stress on adjacent fault segments and nearby faults. These regions of increased stress are prone to failure, generating aftershocks. The aftershocks gradually decrease in frequency and magnitude over time as the crust adjusts to its new configuration. The largest aftershocks typically have magnitudes roughly 1 unit smaller than the main shock, though occasionally an aftershock can equal or exceed the main shock, in which case it is reclassified as the new main shock. Foreshocks sometimes precede major earthquakes, though they can only be identified as foreshocks in retrospect. These are smaller earthquakes that occur on or near the fault that will eventually produce the main shock. Not all earthquakes have foreshocks, and small earthquakes occur frequently in tectonically active areas, making it difficult to determine whether any particular small earthquake is a foreshock or an independent event. This uncertainty limits the ability to predict earthquakes based on foreshock activity. Earthquake prediction: the ability to specify when and where a significant earthquake will occur with enough precision and reliability to guide evacuation or other preparedness actions, remains beyond current scientific capability. While scientists can identify regions at elevated risk based on the history of past earthquakes and the accumulation of stress on known faults, predicting the specific time of an earthquake has proved extremely difficult. Earthquakes appear to be an example of a complex system where small differences in initial conditions can lead to vastly different outcomes, making deterministic prediction impossible with current knowledge and technology. However, earthquake early warning systems can provide seconds to minutes of warning after an earthquake begins, but before strong shaking arrives at a given location. These systems detect the initial seismic waves from an earthquake and rapidly calculate the location and magnitude. Because seismic waves take time to propagate, regions at some distance from the epicenter can receive automated warnings before the strongest shaking arrives, allowing automated systems to shut down critical infrastructure and giving people time to take protective action. Japan, California, Mexico, and other regions have implemented such systems, providing valuable seconds that can save lives and prevent damage. The effects of earthquakes on the surface and on human societies depend on many factors beyond the earthquake's magnitude. The depth of the earthquake matters greatly. Deeper earthquakes produce less intense surface shaking than shallow ones of the same magnitude because the seismic waves must travel farther and lose energy along the way. The local geology affects shaking intensity dramatically. Solid bedrock transmits seismic waves efficiently but does not amplify them much. Soft sediments, especially water-saturated sediments, can amplify seismic waves by factors of 10 or more, causing much stronger shaking than occurs on bedrock at the same distance from the epicenter. The quality of buildings and infrastructure determines how much damage occurs for a given level of shaking. Properly designed and constructed earthquake-resistant buildings can withstand very strong shaking with minimal damage, while poorly constructed buildings may collapse in moderate shaking. The devastating loss of life in some earthquakes reflects not just the earthquake's size, but also the vulnerability of the built environment. The 1999 Izmit earthquake in Turkey and the 2010 Haiti earthquake caused catastrophic damage partly because of inadequate building standards and construction practices. Earthquakes generate several types of surface effects beyond building damage. Landslides can be triggered on steep slopes when shaking reduces the friction holding soil and rock in place. These landslides may dam rivers, creating lakes that can later fail catastrophically and flood downstream areas. Ground liquefaction occurs when water-saturated sandy soil loses strength during shaking, causing it to behave like a liquid. Buildings on liquefied soil can sink or topple, and underground utilities can float to the surface. Surface rupture occurs when the earthquake fault extends to the surface, creating scarps and offset features that directly break the ground surface. Tsunamis represent perhaps the most far-reaching earthquake effect. When an earthquake occurs beneath the ocean and causes vertical displacement of the seafloor, it can generate tsunami waves that propagate across entire ocean basins. In the deep ocean, tsunami waves travel at speeds of several hundred kilometers per hour, but have heights of only a meter or less, making them imperceptible to ships. As the waves approach shallow coastal waters, they slow down but grow dramatically in height, sometimes exceeding 10 meters or more. The 2004 Indian Ocean tsunami killed more than 200,000 people across a dozen countries, demonstrating the devastating reach of this earthquake-generated hazard. Understanding earthquakes as natural expressions of plate motion and crustal adjustment helps contextualize them within Earth's broader geological processes. They represent the inevitable consequence of a dynamic planet where rigid lithospheric plates move over a ductile interior. The stress that drives earthquakes is the same stress that builds mountains, opens ocean basins, and shapes continents. Earthquakes, for all their potential for destruction, are simply the Earth doing its patient work of redistributing stress and accommodating the slow but persistent motion of the plates. In the calm of night, we can reflect on these powerful adjustments as part of the planet's ongoing evolution. Dramatic in human terms, but brief moments in the geological perspective. Seismic waves. Messages traveling through stone. When an earthquake occurs and rock suddenly slips along a fault, the released energy radiates outward through the earth in the form of seismic waves. These waves are vibrations that travel through solid rock, carrying information about the earthquake that generated them and about the materials through which they pass. Understanding seismic waves allows scientists to locate earthquakes, measure their size, and probe the otherwise inaccessible interior of our planet. Seismic waves come in several distinct types, each with different properties and behaviors. The two main categories are body waves, which travel through the interior of the Earth, and surface waves, which travel along Earth's surface. Body waves include P waves and S waves, while surface waves include love waves and Rayleigh waves. Each type moves differently and causes different patterns of ground motion. P waves, or primary waves, are compressional waves similar to sound waves. As a P wave passes through rock, it alternately compresses and extends the material in the direction of wave travel. Imagine a slinky toy stretched between your hands. If you push one end toward the other and then pull it back, a compression pulse travels along the slinky. This is analogous to how P waves propagate through Earth. The rock particles vibrate back and forth in the same direction the wave is traveling, creating alternating regions of compression and rarefaction. P waves are the fastest seismic waves, traveling at speeds between 5 and 8 kilometers per second in Earth's crust and even faster in the deeper mantle and core. Their high speed means they arrive first at seismometers, which is why they are called primary waves. P waves can travel through any material, whether solid, liquid, or gas, because all materials can be compressed. This ability to propagate through liquids becomes important for understanding Earth's interior structure, as P waves can pass through the liquid outer core while S waves cannot. The speed at which P waves travel depends on the properties of the material through which they pass, specifically the density and the elastic moduli that describe how the material responds to compression. Denser materials tend to slow P waves while stiffer materials speed them up. The net effect depends on the balance between these factors. In general, P waves travel faster through cool, rigid rock than through hot, partially molten rock. and faster through crystalline rock than through sediments or soil. S waves, or secondary waves, are shear waves that cause rock particles to move perpendicular to the direction of wave propagation. If you imagine holding one end of a rope and snapping it up and down, a wave travels along the rope while each point on the rope moves up and down perpendicular to the rope's length. This is analogous to S-wave motion. As an S-wave passes through rock, the rock shears or twists, with particles moving perpendicular to the wave's travel direction. S-waves travel more slowly than P-waves, typically at speeds between 3 and 4.5 kilometers per second in the crust. They arrive at seismometers after P-waves, hence the name secondary waves. Crucially, S-waves cannot propagate through liquids or gases because these materials cannot support shear stress. When you try to shear a liquid, it simply flows rather than transmitting the shear as an elastic wave. This property of S-waves provides critical information about Earth's interior. The observation that S-waves from earthquakes do not appear on seismometers on the opposite side of Earth, while P-waves do, revealed that Earth has a liquid outer core through which S-waves cannot pass. The arrival time difference between P-waves and S-waves at a seismometer allows scientists to estimate the distance to an earthquake. Because P-waves travel faster, they arrive first. The farther away the earthquake, the longer the time gap between P-wave and S-wave arrivals. By measuring this time difference, a seismologist can calculate how far away the earthquake occurred. Using data from 3 or more seismometers at different locations, the earthquake's epicenter can be triangulated by finding the point that is the correct distance from each station. Surface waves travel along Earth's surface rather than through its interior. They form when body waves reach the surface and are partially converted into waves that propagate along the interface between rock and air or water. Surface waves travel more slowly than body waves, but often cause stronger ground motion and more damage because their energy is confined to a thin layer near the surface rather than spreading through a large volume. Love waves, named after the mathematician Augustus Love, who first described them mathematically, cause horizontal ground motion perpendicular to the wave's direction of propagation. Imagine a snake slithering along the ground, moving side to side. Love waves cause a similar side-to-side shaking of the ground surface. These waves are particularly damaging to foundations and structures because the horizontal motion can cause buildings to sway violently. Rayleigh waves, named after Lord Rayleigh who predicted their existence, cause ground motion that combines vertical and horizontal components in an elliptical pattern. As a Rayleigh wave passes a point on the surface, the ground traces out an ellipse, rising and falling while also moving horizontally. The motion is similar to waves on the ocean, where water particles move in circular or elliptical orbits as the wave passes. Rayleigh waves are often the slowest seismic waves but carry significant energy and can cause strong shaking that lasts for several minutes during large earthquakes. The amplitude and frequency content of seismic waves provide information about the earthquake and the path the waves traveled. Large earthquakes generate waves with larger amplitudes, meaning greater displacement of the ground. The magnitude scales used to measure earthquake size are based fundamentally on the amplitude of seismic waves recorded at standard distances. The original Richter scale, developed in the 1930s for Southern California earthquakes, was defined based on the maximum amplitude recorded on a specific type of seismometer at a distance of 100 kilometers from the epicenter. Modern magnitude scales, particularly the moment magnitude scale, use more sophisticated analysis of the entire seismogram to calculate the total energy released by the earthquake. The moment magnitude scale directly relates to the physical properties of the earthquake, the area of the fault that slipped, the average amount of slip, and the rigidity of the rock. This scale does not saturate at high magnitudes like older scales, making it appropriate for the largest earthquakes. An earthquake's moment magnitude can be calculated from the seismic waves it generates, allowing scientists to determine the size of earthquakes anywhere in the world within minutes of their occurrence. The frequency content of seismic waves reflects both the earthquake source and the path the waves traveled. Small earthquakes generate predominantly high-frequency waves, causing rapid shaking that feels sharp and jolting. Large earthquakes generate more low-frequency energy, causing slow, rolling shaking that can last for minutes. As waves propagate through Earth, higher frequencies are preferentially absorbed and scattered, while lower frequencies travel farther with less attenuation. This is why distant earthquakes, when felt, produce gentle rolling motion rather than sharp jolting. Seismic waves refract and reflect at boundaries between layers with different properties. When a wave encounters a boundary between rock types with different densities or elastic properties, part of the wave continues through the boundary but at a different angle, while part reflects back. This is similar to how light refracts when passing from air into water and partly reflects off the water surface. By analyzing how seismic waves refract and reflect at boundaries deep within Earth, seismologists can map the internal structure of the planet without directly observing it. The discovery of Earth's layered structure came largely from seismic wave analysis. In 1906, Richard Dixon Oldham identified distinct P-wave and S-wave arrivals on seismograms and noted that P-waves passing through Earth's core were delayed, indicating the core had different properties than the mantle. In 1914, Benno Gutenberg more precisely determined the depth of the core-mantle boundary at 2,900 kilometers by analyzing the pattern of seismic wave arrivals around the world. In 1936, Inge Lehmann discovered that P-waves behaved in ways that required a solid inner core within the liquid outer core, explaining seismogram complexities that previous models could not. Seismic tomography, a technique analogous to medical CT scanning, uses the travel times of seismic waves from many earthquakes to thousands of seismometers to create three-dimensional images of Earth's interior. Just as a CT scan reveals structures inside the human body by measuring how X-rays pass through different tissues, seismic tomography reveals structures inside Earth by measuring how seismic waves travel at different speeds through different regions. Regions where waves travel faster than average indicate cool, rigid rock, while regions where waves travel more slowly indicate hot or partially molten rock. This technique has revealed the fate of subducted oceanic lithosphere, showing cold slabs that have descended through the mantle and piled up on the core mantle boundary. It has revealed hot upwellings beneath volcanic hotspots like Hawaii and Iceland. It has shown lateral variations in temperature and composition throughout the mantle, providing insights into how mantle convection operates and how heat escapes from Earth's interior. Free oscillations represent another class of seismic phenomena. When a very large earthquake occurs, it can set the entire Earth vibrating, rather like ringing a bell. These free oscillations involve the whole planet oscillating at specific frequencies determined by Earth's size, mass distribution, and elastic properties. The oscillations have periods of minutes to hours and can be detected by sensitive seismometers for days after a great earthquake. Analysis of free oscillations provides information about Earth's average properties and has helped constrain models of the planet's internal structure. The attenuation of seismic waves, the gradual loss of amplitude as they propagate, provides information about the physical state of Earth's interior. Seismic waves lose energy through several mechanisms. Geometric spreading as the wave front expands, scattering by small-scale heterogeneities and absorption where wave energy converts to heat. The rate of absorption depends on temperature and the presence of partial melt. Regions with high attenuation are often interpreted as hot or partially molten, while regions with low attenuation are cool and fully solid. Understanding seismic waves allows earthquake early warning systems to function. The P wave arriving first can trigger automated alerts before the more damaging S waves and surface waves arrive. Though the warning time may be only seconds to tens of seconds, this is enough for automated systems to shut down gas lines, halt trains, and execute other protective actions. People receiving warnings can take cover before strong shaking begins, potentially saving lives. Seismic monitoring networks around the world continuously record ground motion, detecting and locating thousands of earthquakes every day. The data flows to analysis centers that calculate earthquake locations, magnitudes, and focal mechanisms within minutes, disseminating information to emergency responders and the public. This global seismic network serves both practical purposes in earthquake monitoring and scientific purposes in studying Earth's interior structure and dynamics. In the quiet of the evening, we can contemplate how these invisible vibrations traveling through solid rock at kilometers per second carry messages about our planet's interior and about the sudden release of stress along distant faults. The waves propagate according to physical laws, refracting and reflecting at boundaries, attenuating as they travel, their behavior revealing the properties of the materials through which they pass. Seismic waves connect the deep interior of our planet to the surface, making the invisible visible through careful analysis and allowing us to understand Earth's structure and dynamics in ways that would otherwise be impossible. The Ring of Fire, a circle of transformation. The Ring of Fire is a vast arc of volcanic and seismic activity that encircles the Pacific Ocean, stretching for approximately 40,000 kilometers along the boundaries of the Pacific tectonic plate. This region contains roughly 75% of Earth's active volcanoes and experiences approximately 90% of the world's earthquakes. The Ring of Fire is not a single continuous feature, but rather a series of subduction zones, volcanic arcs, and associated features that together form a ring-like pattern when viewed on a map of the Pacific Basin. The western edge of the Ring of Fire extends along the eastern coasts of Asia and Oceania. Beginning in the north, it includes the volcanoes of Kamchatka in far eastern Russia, where the Pacific Plate subducts beneath the North American and Eurasian plates. Proceeding southward, the ring continues through the Kuril Islands, Japan, and the Philippines, where multiple subduction zones create complex patterns of volcanic arcs and deep ocean trenches. The Japanese archipelago sits above a particularly active section of the Ring of Fire, where the Pacific Plate and Philippine Sea Plate both subduct beneath the Eurasian Plate, creating the conditions for frequent earthquakes and volcanic eruptions that have shaped Japanese history and culture. Continuing southward, the Ring of Fire passes through Indonesia, a region of extraordinary volcanic activity where the Indo-Australian Plate subducts beneath the Eurasian Plate. Indonesia contains more active volcanoes than any other nation, with over 130 volcanic edifices showing recent activity. The 1815 eruption of Mount Tambora in Indonesia produced the largest volcanic eruption in recorded history, ejecting so much ash and sulfur dioxide into the stratosphere that it caused global cooling and crop failures, leading to 1816 being remembered as the year without a summer in many parts of the world. The Ring of Fire continues through Papua New Guinea and the Solomon Islands, where the Pacific Plate interacts with the Indo-Australian Plate in a complex zone of subduction and crustal deformation. The region contains numerous active volcanoes built on island arcs, chains of volcanic islands formed above subduction zones. These island arcs represent locations where oceanic lithosphere of one plate subducts beneath oceanic lithosphere of another plate, creating volcanic islands rather than the volcanic mountain ranges that form when oceanic lithosphere subducts beneath continental lithosphere. The southwestern portion of the Ring of Fire extends through Vanuatu, New Zealand, and the Kermadec and Tonga Island arcs. New Zealand sits at the boundary between the Pacific and Indo-Australian plates and the country experiences both subduction zone volcanism and volcanism associated with crustal extension in the Taupo volcanic zone on the North Island. The region's geological complexity creates a diverse volcanic landscape, from the symmetrical stratovolcanoes to large calderas that have produced massive eruptions in the geological past. The eastern edge of the Ring of Fire runs along the western coasts of the Americas. Beginning in the south, the Nazca Plate subducts beneath the South American Plate, creating the volcanic arc of the Andes Mountains. The Andes represent one of the longest volcanic chains on Earth, with numerous active volcanoes distributed along the western margin of South America from southern Chile northward to Colombia. The subduction of the Nazca Plate beneath South America also generates powerful earthquakes, including the 1960 Chilean earthquake, the largest earthquake ever recorded by seismometers at magnitude 9.5. Proceeding northward, the Ring of Fire continues through Central America, where the Cocos Plate subducts beneath the Caribbean Plate, creating active volcanoes in Costa Rica, Nicaragua, El Salvador, Guatemala, and southern Mexico. Many of these volcanoes rise as steep stratovolcanoes above the surrounding landscape, their presence a constant reminder of the active plate boundary beneath. The northern portion of the eastern Ring of Fire extends through Mexico, where the Cocos and Rivera Plates subduct beneath the North American Plate and continues into the Pacific Northwest of the United States and Canada. The Cascade Range, extending from Northern California through Oregon and Washington into British Columbia, contains numerous active volcanoes, including Mount St. Helens, which erupted explosively in 1980, and Mount Rainier, considered one of the most dangerous volcanoes in North America due to its proximity to heavily populated areas around Seattle and Tacoma. The Ring of Fire completes its circuit through the Aleutian Islands of Alaska, where the Pacific Plate subducts beneath the North American Plate. The Aleutian Arc contains dozens of active volcanoes spread across the islands, many of them erupting regularly. The region experiences frequent earthquakes, including some of the largest earthquakes recorded in North America. The 1964 Alaska earthquake, magnitude 9.2, generated tsunamis that affected coastal communities around the Pacific Basin, demonstrating the far-reaching impacts of Ring of Fire seismic events. The concentration of volcanic and seismic activity in the Ring of Fire reflects the fundamental processes of plate tectonics. Subduction zones dominate the Ring of Fire, and subduction is inherently associated with both volcanism and earthquakes. When oceanic lithosphere descends into the mantle at subduction zones, it releases water that triggers melting in the overlying mantle wedge, creating magma that rises to form volcanoes. Simultaneously, the friction and stress associated with one plate grinding beneath another generates frequent earthquakes, ranging from small tremors to the largest earthquakes Earth can produce. The Pacific Plate, largely oceanic, is surrounded by subduction zones where it descends beneath neighboring plates. This configuration creates the ring-like pattern of activity around the Pacific Ocean's margins. The Atlantic Ocean, by contrast, lacks such a ring because the Atlantic is opening at a mid-ocean ridge while the Pacific is closing as subduction consumes old oceanic lithosphere around its edges. This fundamental difference in plate configuration explains why the Atlantic Basin experiences relatively little volcanic and seismic activity compared to the Pacific. The Ring of Fire is not static but evolves over geological time. As plates move and their configurations change, the patterns of volcanism and seismicity shift. Volcanic arcs migrate as subduction angles change. New subduction zones form while old ones cease activity. Over tens of millions of years, the entire geography of the Ring of Fire will change as the Pacific Plate continues to shrink, and the continents surrounding it drift to new positions. Despite the hazards it poses, the Ring of Fire has provided benefits to the societies that have developed along its margins. Volcanic soils derived from weathered volcanic ash are often remarkably fertile, supporting productive agriculture in regions that might otherwise have less favorable soils. Geothermal energy, generated by the heat from magma chambers beneath active volcanic regions, provides clean, renewable power in countries like New Zealand, the Philippines, Indonesia, and several Central American nations. Hot springs and geothermal features associated with Ring of Fire volcanism create tourist attractions and provide therapeutic uses. The Ring of Fire has profoundly shaped human history and culture in the regions it affects. Volcanic eruptions have destroyed cities and altered the course of civilizations, from Pompeii's burial by Vesuvius to the cultural impacts of major eruptions in Japan and Indonesia. Earthquakes have repeatedly challenged societies along the Ring of Fire to develop resilient infrastructure and emergency response systems. The constant presence of geological hazards has influenced religion, mythology, architecture, and social organization in Ring of Fire societies, creating cultural adaptations to life on an active plate boundary. Scientific understanding of the Ring of Fire has advanced dramatically over the past century. The recognition that the ring-like pattern of activity reflects plate tectonic boundaries represented a key insight in the development of plate tectonic theory in the 1960s. Modern monitoring networks track earthquake and volcanic activity around the Ring of Fire in real time, providing data for both hazard assessment and scientific research. International collaborations share information and expertise, recognizing that the hazards transcend national boundaries and that understanding gained in one region can benefit others. Looking toward the future, the Ring of Fire will remain a zone of intense geological activity for millions of years to come. The plate motions that drive the activity will continue at their patient pace of centimeters per year, accumulating strain that will eventually release in earthquakes and feeding magma chambers that will eventually erupt. Societies around the Ring of Fire continue to adapt, building more earthquake-resistant structures, improving volcanic monitoring and early warning systems, and developing emergency preparedness plans that save lives when disasters occur. In the peaceful darkness, we can reflect on the Ring of Fire as a manifestation of Earth's dynamic nature, a visible expression of the forces that shape our planet's surface. The volcanoes and earthquakes that characterize the ring are not random calamities but predictable consequences of plate tectonic processes operating according to physical laws. The ring encircles an ocean, connects continents, and demonstrates how local geological processes can create patterns that span the entire planet. Understanding the Ring of Fire helps us understand Earth as an integrated system where processes in one region connect to and influence processes elsewhere, all part of the grand story of a dynamic planet continuously reshaping itself. Measuring and understanding, scales and instruments. To study earthquakes scientifically and communicate their size and effects, researchers have developed measurement scales and sophisticated instruments that detect and record ground motion. These tools allow seismologists to monitor Earth's seismic activity continuously, comparing earthquakes across different regions and time periods, and building understanding of earthquake processes through quantitative analysis. The measurement of earthquake size has evolved considerably over the past century. The first widely used magnitude scale, developed by Charles Richter in 1935, was designed specifically for earthquakes in Southern California recorded on a particular type of seismometer. The Richter scale defined magnitude based on the logarithm of the maximum amplitude of seismic waves recorded at a standard distance from the epicenter. Each unit increase in Richter magnitude represents a 10-fold increase in measured amplitude and roughly 32 times more energy release. The original Richter scale worked reasonably well for local earthquakes in California, but had limitations when applied to larger or more distant earthquakes. It saturated at magnitudes around 7, meaning that earthquakes larger than this would all measure approximately the same magnitude even though they actually released very different amounts of energy. This saturation occurred because the seismometers and methods used for the original scale could not adequately capture the long-period seismic waves generated by the largest earthquakes. To address these limitations, seismologists developed additional magnitude scales for different types of seismic waves and different distance ranges. Surface wave magnitude scales use the amplitude of surface waves rather than body waves. Body wave magnitude scales focused on P waves or S waves at teleseismic distances. Each scale had its own useful range of applicability, but the proliferation of different scales created confusion when comparing earthquakes measured on different scales. The moment magnitude scale, developed in 1970s and widely adopted by the 1990s, resolved these issues by basing magnitude directly on the physical properties of the earthquake source. The moment magnitude relates to the seismic moment, which equals the product of the fault area that slipped, the average amount of slip, and the rigidity of the rock. This physical definition means the scale does not saturate and can accurately represent the size of the largest earthquakes. A magnitude 9 earthquake releases 32 times more energy than a magnitude 8, which in turn releases 32 times more energy than a magnitude 7. The moment magnitude scale is now the standard for reporting earthquake sizes, though it requires more detailed analysis of seismograms than older scales. For smaller earthquakes, moment magnitude gives similar values to Richter magnitude, providing continuity with historical catalogs. For the largest earthquakes, moment magnitude can distinguish between events that older scales would have rated similarly, providing a more accurate representation of their actual size and energy release. Intensity scales measure the effects of earthquakes at specific locations rather than the size of the earthquake itself. The modified Mercalli intensity scale, widely used in the United States, ranges from intensity 1, not felt except by very few people under favorable conditions, to intensity 12, total destruction with objects thrown into the air and large-scale changes to the landscape. Intensity depends not only on the earthquake's magnitude but also on distance from the epicenter, local geological conditions, and building construction quality. A single earthquake produces different intensities at different locations, with intensities generally decreasing with distance from the epicenter but showing local variations due to soil conditions and topography. Intensity maps, showing the distribution of observed effects from an earthquake, provide valuable information about ground motion patterns and help identify areas where site conditions amplified shaking. Modern intensity maps are created quickly after significant earthquakes by collecting reports from people who felt the shaking through online systems, supplementing traditional field surveys with crowdsourced data that can be gathered within minutes of an earthquake. Seismometers, the instruments that detect and record ground motion, have evolved from simple mechanical devices to sophisticated electronic systems. The basic principle remains consistent across different designs. A mass is suspended in a way that allows it to remain relatively stationary, while the ground beneath it moves. The relative motion between the mass and the ground is recorded, providing a measure of ground motion. Traditional mechanical seismometers used a suspended mass attached to a pen that drew on a rotating drum covered with paper. When the ground shook, the drum moved with the ground while the mass and pen remained relatively stationary, causing the pen to draw a wavy line showing the ground motion. These seismograms provided permanent records of earthquakes that could be analyzed to determine the earthquake's location, magnitude, and characteristics. Modern seismometers use electronic sensors to detect motion and digital recording systems to store the data. Broadband seismometers can accurately record ground motion across a wide range of frequencies, from the very low frequencies of free oscillations with periods of tens of minutes to the high frequencies of local earthquakes with periods of fractions of a second. This broad frequency response allows a single instrument to capture all the information in seismic waves, from local micro-earthquakes to the largest earthquakes occurring on the opposite side of the planet. Strong motion instruments designed to record the intense shaking near large earthquakes use accelerometers that measure ground acceleration rather than displacement or velocity. These instruments can remain on scale during very strong shaking that would overwhelm sensitive seismometers designed for detecting distant or small earthquakes. Strong motion data are essential for earthquake engineering, providing measurements of the actual ground motion that structures must withstand. Seismometer networks around the world operate continuously, with data flowing to analysis centers in real time. The global seismographic network consists of more than 150 stations distributed around the globe, each equipped with broadband seismometers and continuous data telemetry. Regional networks in seismically active areas contain hundreds to thousands of seismometers, providing dense coverage that allows precise location of even small earthquakes. Automated systems analyze incoming seismic data, detecting earthquakes and calculating preliminary locations and magnitudes within minutes. These rapid determinations are crucial for tsunami warning systems and earthquake early warning. Human analysts then review the automated solutions, refining them and adding additional information such as focal mechanisms that show the orientation of the fault and the direction of slip. GPS measurements provide complementary information about ground deformation. While seismometers record rapid ground motion during earthquakes, GPS stations measure the permanent displacement that results from earthquakes and the gradual deformation that occurs between earthquakes as stress accumulates. Networks of continuously operating GPS stations track plate motions and identify areas where the crust is actively deforming, helping scientists understand where stress is accumulating and where future earthquakes are most likely. Satellite radar interferometry, comparing radar images of the ground taken at different times, can map the pattern of ground deformation caused by earthquakes with remarkable detail. These measurements show how the ground surface moved during an earthquake, providing constraints on the fault geometry and slip distribution that complement the information from seismic waves. Ocean bottom seismometers extend monitoring capabilities to the seafloor, where most of Earth's seismic activity actually occurs along mid-ocean ridges and subduction zones. These instruments operate autonomously on the seafloor for months to years, recording earthquakes and then returning to the surface for data recovery. The data from ocean bottom seismometers reveal the detailed patterns of seismicity at undersea plate boundaries and improve the ability to locate and characterize these submarine earthquakes. The wealth of seismic data accumulated over decades enables statistical analyses that reveal patterns in earthquake occurrence. Researchers study how earthquake rates vary over time, how aftershocks decay following main shocks, and how stress changes from one earthquake affect the likelihood of subsequent earthquakes. These studies contribute to probabilistic earthquake forecasting, which estimates the likelihood of earthquakes of various sizes occurring in specific regions over specific time periods. Earthquake catalogs document all detected earthquakes with their locations, magnitudes, depths, and timing. These catalogs extend back more than a century for some regions, providing historical records that reveal long-term patterns. Analysis of these catalogs shows that some faults rupture regularly with characteristic intervals between earthquakes, while others show more random behavior. Some regions experience swarms of many earthquakes in short periods, while others have more isolated events. Understanding these patterns helps assess earthquake hazards and informs building codes and preparedness planning. The combination of improved instrumentation, denser monitoring networks, and more sophisticated analysis techniques has transformed earthquake science over the past several decades. Earthquakes that once would have been described only in qualitative terms can now be characterized quantitatively in terms of magnitude, location, depth, focal mechanism, and moment release. The rapid processing and dissemination of earthquake information serves both scientific research and practical hazard mitigation, demonstrating how advances in measurement and analysis translate directly into societal benefits. In the stillness of evening, we can appreciate how these instruments and scales allow humanity to quantify and understand phenomena that would otherwise remain mysterious. The careful measurement of earthquake size and effects, the continuous monitoring of Earth's seismic activity, and the analysis of decades of accumulated data reveal patterns and processes that help us coexist with geological hazards. Through patient observation and rigorous analysis, scientists have transformed earthquakes from inexplicable catastrophes into comprehensible natural phenomena that, while still dangerous, can be studied, measured, and to some degree anticipated. The beneficial side: gifts from geological activity. While volcanoes and earthquakes often capture attention for their destructive potential, these same geological processes provide substantial benefits that have sustained human civilizations for millennia. The heat flowing from Earth's interior, manifested through volcanic activity, creates resources that modern societies harness for energy, agriculture, and economic development. Understanding these benefits provides a more complete perspective on the role of geological activity in shaping human environments. Volcanic soils rank among the most fertile in the world, supporting productive agriculture in regions that might otherwise struggle with poor soil quality. When volcanic ash falls across the landscape during eruptions, it initially appears destructive, burying crops and smothering vegetation. Over time, however, the ash weathers and breaks down, releasing minerals and nutrients that enrich the soil. Volcanic materials contain abundant minerals including potassium, phosphorus, calcium, magnesium, and trace elements essential for plant growth. The weathering of volcanic rocks produces clay minerals with excellent water retention properties, helping soils maintain moisture during dry periods. The porous structure of weathered volcanic materials improves soil drainage and aeration, preventing waterlogging while maintaining adequate moisture. The dark color of many volcanic soils helps them absorb solar heat, warming more quickly in spring and extending growing seasons in cooler climates. Regions with volcanic soils often support dense human populations sustained by productive agriculture. The island of Java in Indonesia, blanketed with ash from dozens of active volcanoes, supports one of the highest population densities on Earth, with much of the population engaged in agriculture on the fertile volcanic soils. The slopes of Mount Etna in Sicily have been cultivated for thousands of years, producing grapes, olives, citrus fruits, and other crops that benefit from the rich volcanic soil. The volcanic soils of the Pacific Northwest support productive forests and agriculture, from apple orchards to vineyards. The benefits of volcanic soils must be weighed against the hazards of living near active volcanoes. Throughout history, people have made this calculation and often chosen to remain in volcanic regions, accepting the periodic hazards in exchange for the ongoing agricultural benefits. This choice reflects the reality that volcanic eruptions, while dangerous, occur infrequently compared to the annual growing seasons that benefit from fertile soils. Geothermal energy represents another major benefit of volcanic activity. In regions where magma chambers lie relatively close to the surface, the immense heat can be harnessed to generate electricity and provide direct heating. Water circulating through hot rocks absorbs heat, and this hot water or steam can be brought to the surface through wells. The steam can drive turbines to generate electricity, or the hot water can be used directly for heating buildings, growing crops in greenhouses, or industrial processes. Iceland derives roughly 1/4 of its electricity and most of its heating from geothermal sources. The country sits on the mid-Atlantic ridge where volcanic activity provides abundant geothermal heat near the surface. Geothermal power plants tap into this heat, providing clean, renewable energy that has freed Iceland from dependence on imported fossil fuels for these purposes. Nearly 90% of Icelandic homes are heated with geothermal water, piped from geothermal fields to urban areas. The Philippines, Indonesia, New Zealand, Italy, and several Central American countries also generate significant electricity from geothermal resources, all in regions of active volcanism along plate boundaries. The United States has substantial geothermal generating capacity in California, Nevada, and Hawaii, with the largest concentration in the Geysers geothermal field north of San Francisco. These geothermal resources provide baseload power that operates continuously, unlike solar and wind, which vary with weather and time of day. Geothermal energy produces minimal greenhouse gas emissions compared to fossil fuels, making it attractive as societies seek to reduce carbon emissions. The fuel source, Earth's internal heat, is effectively inexhaustible on human timescales, providing a sustainable energy source for regions with access to geothermal resources. As technology improves, enhanced geothermal systems may allow exploitation of geothermal resources in regions without natural hydrothermal systems, potentially expanding access to this clean energy source. Hot springs and geothermal features associated with volcanism provide recreational, therapeutic, and cultural benefits. Cultures around the world have used natural hot springs for bathing, relaxation, and healing for thousands of years. The mineral content of geothermal waters varies depending on the rocks through which they circulated, and some hot springs are valued for specific mineral content thought to have therapeutic properties. Japan's onsen culture, centered on natural hot springs, reflects the integration of geothermal features into daily life and recreation. Iceland's Blue Lagoon, a geothermal spa formed in the outflow from a geothermal power plant, has become one of the country's most popular tourist destinations. Yellowstone's geothermal features, including geysers, hot springs, and mud pots, attract millions of visitors annually, contributing substantially to the regional economy. Volcanic landscapes create spectacular scenery that draws tourists and supports economies in volcanic regions. The volcanic peaks of the Cascades, the calderas of the Andes, the crater lakes of East Africa, and the lava fields of Hawaii attract visitors who appreciate these dramatic manifestations of geological processes. Volcanic eruptions themselves, when they can be safely observed, draw volcano tourists who travel to witness these awe-inspiring natural phenomena. Mineral deposits associated with volcanic and magmatic processes have provided resources that enabled technological development throughout human history. Copper, gold, silver, zinc, lead, and many other metals concentrate in hydrothermal systems associated with magma chambers. As hot water circulates through the rocks surrounding a magma body, it dissolves metals and minerals. When the water cools or encounters rocks that cause chemical changes, the dissolved metals precipitate, forming concentrated ore deposits. Many of the world's major mining districts occur in volcanic belts or ancient volcanic regions where erosion has exposed the mineralized rocks. The copper deposits of the Andes, formed by hydrothermal systems above subducting slabs, support major mining industries in Chile and Peru. Gold deposits in the western United States, Australia, and elsewhere formed in volcanic and magmatic environments. These mineral resources have been essential to economic development, providing materials for technology, construction, and manufacturing. Obsidian, volcanic glass formed when lava cools so rapidly that crystals cannot grow, was valued by ancient peoples for making sharp tools and weapons. Obsidian blades can be sharper than modern surgical scalpels, and archaeological evidence shows obsidian was traded across long distances in the ancient world. Pumice, the frothy volcanic rock full of gas bubbles, has commercial uses from construction to cosmetics to horticulture. Volcanic rocks themselves provide construction materials. Basalt and andesite serve as building stone and road aggregate. Volcanic ash and pumice are used in cement and concrete, providing properties that improve durability and reduce weight. Roman concrete, renowned for its longevity, utilized volcanic ash from Italian volcanoes, and structures built with this concrete still stand 2,000 years later. The study of volcanic and earthquake processes advances scientific understanding of Earth's interior and dynamics. Every earthquake provides data about Earth's structure as seismic waves propagate through the planet. Every eruption provides samples of material from depth and information about magmatic processes. The continuous monitoring of volcanic and seismic activity generates data that improve understanding of plate tectonics, mantle convection, and the mechanisms of earthquakes and eruptions. This scientific knowledge has practical applications beyond understanding the phenomena themselves. Insights gained from studying earthquake physics inform building codes and engineering standards that save lives. Understanding volcanic processes helps develop monitoring techniques that provide early warning of eruptions. The global networks of seismometers and volcanic monitoring stations serve both scientific research and hazard mitigation, demonstrating how basic research and practical applications support each other. The benefits of geological activity emerge from the same fundamental processes that create hazards. The heat-driving volcanic eruptions also powers geothermal energy systems and weathers volcanic rocks into fertile soil. The plate motions generating earthquakes also drive mountain building, ocean basin formation, and the recycling of crustal materials that maintain Earth's habitability over geological time. Understanding both the hazards and benefits provides a balanced perspective that recognizes geological activity as a fundamental aspect of Earth as a dynamic planet. In the gentle evening, we can reflect on how Earth's internal heat, escaping through volcanoes and driving the motions that generate earthquakes, has shaped the environment in which human civilization developed. The fertile volcanic soils that feed populations, the geothermal energy that powers societies, the mineral resources that enabled technological advancement, and the spectacular landscapes that inspire wonder all flow from the same geological processes that occasionally manifest in destructive events. These processes, operating over billions of years, have made Earth the dynamic, life-supporting planet it is, continuously reshaping the surface and moving materials between the deep interior and the surface in the grand cycles that define our world. Living with dynamic Earth. Adaptation and perspective. Humanity has lived alongside volcanic and seismic hazards throughout its history, developing strategies for coexistence that balance the risks against the benefits of inhabiting geologically active regions. The relationship between human societies and geological hazards reveals much about adaptation, resilience, and our species' capacity to thrive in dynamic environments. Understanding this relationship provides perspective on how communities prepare for, respond to, and recover from geological events. Modern societies employ multiple approaches to reduce earthquake and volcanic hazards. Engineering solutions focus on designing and constructing buildings and infrastructure that can withstand strong shaking without collapsing. Earthquake-resistant design has evolved considerably over the past century, incorporating flexible structures that can absorb and dissipate seismic energy, damping systems that reduce shaking amplitude, and base isolation systems that partially decouple buildings from ground motion. Building codes in seismically active regions specify design standards based on the expected intensity of shaking. These codes are continuously refined as engineers learn from earthquake damage and as understanding of ground motion improves. Older buildings constructed before modern codes often require retrofitting to improve earthquake resistance. This process, while expensive, substantially reduces casualties and damage when earthquakes occur. The effectiveness of earthquake-resistant construction is evident when comparing damage patterns between regions with different building standards. Modern, well-designed buildings can survive even very strong shaking with limited damage, protecting occupants and maintaining functionality. The same intensity of shaking can collapse poorly constructed buildings, causing catastrophic loss of life. The contrast demonstrates that earthquake hazards largely result not from the earthquakes themselves, but from the interaction between earthquakes and the built environment. Land use planning provides another tool for hazard reduction. Avoiding construction in areas most susceptible to landslides, liquefaction, or fault rupture reduces exposure to these specific hazards. Maintaining open spaces and parks in high-hazard zones provides community benefits while avoiding the concentration of vulnerable structures. Zoning regulations can restrict certain types of development in hazardous areas while allowing uses that pose less risk. Volcanic hazard management focuses on monitoring active volcanoes and maintaining evacuation plans. Modern volcano observatories continuously monitor seismic activity, ground deformation, gas emissions, and other signs that indicate magma movement beneath volcanoes. When these signals suggest an eruption may be imminent, authorities can issue warnings and initiate evacuations, moving people out of harm's way before the eruption occurs. The successful prediction and evacuation before the 1991 eruption of Mount Pinatubo in the Philippines demonstrated the value of volcano monitoring. Scientists detected increasing seismic activity and ground deformation in the months before the eruption, leading to evacuations that saved thousands of lives. Though the eruption was one of the largest of the 20th century, casualties were limited because communities in the highest risk areas had been evacuated. Education and preparedness help individuals and communities respond effectively when earthquakes or eruptions occur. Earthquake drills teach people to drop, cover, and hold on when shaking begins, reducing injuries from falling objects and building collapse. Emergency supply kits allow families to sustain themselves if infrastructure is damaged and service is disrupted. Community emergency response teams train volunteers to assist in the immediate aftermath of disasters, supplementing professional emergency services that may be overwhelmed. The psychological aspects of living with geological hazards merit consideration. Communities in seismically active regions develop cultural adaptations that acknowledge the hazards while maintaining normal life. In Japan, earthquake drills occur regularly in schools and workplaces, integrating preparedness into routine activities. Traditional architecture in some volcanic regions incorporates features that provide protection from ashfall or pyroclastic flows, reflecting generations of experience with volcanic hazards. The relationship between hazard frequency and societal response is complex. Regions experiencing frequent small to moderate earthquakes tend to maintain higher levels of preparedness because the hazard feels immediate and real. Regions where large earthquakes occur only every few centuries may experience complacency, as generations pass without direct experience of major events. Maintaining preparedness over long intervals between major earthquakes challenges societies, requiring sustained commitment to prevention and preparation even when the hazard seems distant. Historical perspective reveals that recovery from even catastrophic events is possible, though the process may span years or generations. Cities destroyed by earthquakes or volcanic eruptions have been rebuilt, often incorporating lessons learned to reduce vulnerability to future events. The recovery process can catalyze improvements in infrastructure, building standards, and emergency response capabilities that leave communities more resilient than before. The economic impacts of geological hazards extend beyond immediate damage. Business interruption, supply chain disruption, and loss of tourism can affect economies for years after major events. The 2011 Tohoku earthquake and tsunami in Japan disrupted global supply chains as manufacturing facilities remained closed and transportation infrastructure required repair. Insurance systems help distribute economic losses across broader populations and over longer time periods, though ensuring adequate coverage in high-hazard areas remains challenging. International cooperation strengthens capacity to respond to geological disasters. When earthquakes or volcanic eruptions exceed the ability of affected countries to respond with local resources, international assistance provides search and rescue teams, medical care, temporary shelter, and reconstruction support. The sharing of scientific knowledge and monitoring technology helps countries develop their own hazard assessment and early warning capabilities. Global networks of seismic and volcanic monitoring stations generate data that benefit all nations. By improving understanding of Earth processes and hazards, the concept of acceptable risk recognizes that eliminating geological hazards is impossible, and that societies make implicit or explicit decisions about the level of risk they will tolerate. These decisions involve trade-offs between the costs of hazard mitigation and the benefits of inhabiting geologically active regions. Complete safety would require abandoning volcanically and seismically active regions, sacrificing the agricultural, economic, and cultural benefits of these areas. Instead, societies invest in mitigation measures that reduce risk to acceptable levels, while maintaining the ability to inhabit and benefit from geologically dynamic regions. Long-term geological perspective reminds us that present patterns of volcanic and seismic activity represent a moment in Earth's ongoing evolution. Plate boundaries migrate over millions of years. Volcanic arcs shift position as subduction zone geometries change. Mountain ranges rise and erode away. The hazards we experience today will eventually move elsewhere as plate tectonics continues its work of reshaping Earth's surface. This perspective does not diminish present hazards, but contextualizes them within the grand timescales of geological change. The study of past earthquakes and eruptions preserved in geological records and historical accounts provides data for assessing future hazards. Paleoseismology, the study of prehistoric earthquakes recorded in geological features, extends earthquake histories back thousands of years beyond written records. The timing and size of past earthquakes on a fault help estimate when the next major earthquake might occur, and how large it might be. Similarly, studying past eruptions preserved in volcanic deposits helps volcanologists assess the range of possible eruptive behaviors at a given volcano. Climate interactions with volcanic activity demonstrate how geological processes affect the entire Earth system. Large volcanic eruptions inject sulfur dioxide into the stratosphere, where it forms sulfate aerosols that reflect sunlight and cool the planet. The 1815 Tambora eruption caused global cooling that lasted several years. Understanding these interactions helps climate scientists account for volcanic influences when modeling climate change and predicting future climate. The relationship between volcanic carbon dioxide emissions and atmospheric carbon dioxide levels operates on geological timescales. Volcanic outgassing has contributed carbon dioxide to the atmosphere throughout Earth history, playing a role in maintaining greenhouse warming that keeps Earth habitable. However, volcanic carbon dioxide emissions, roughly 200 million tons per year globally, are less than 1% of current human carbon dioxide emissions. On geological timescales measured in millions of years, volcanic outgassing balances chemical weathering that removes carbon dioxide from the atmosphere, maintaining long-term habitability. Technological advances continue to improve hazard assessment and mitigation. Satellite monitoring of ground deformation provides detailed data on volcanic inflation and earthquake-related movements. Machine learning algorithms analyze seismic data to detect subtle patterns that might indicate increased hazard. Low-cost seismic sensors expand monitoring networks in regions with limited resources. Improved communication systems rapidly disseminate warnings to affected populations. These technological capabilities, combined with scientific understanding and engineering solutions, progressively reduce the vulnerability of societies to geological hazards. The future will bring continued volcanic eruptions and earthquakes as plate tectonics continues its patient work. The hazards these events pose will persist, but human capacity to understand, prepare for, and respond to them continues to improve. Communities learning from past events implement measures that reduce future impacts. Science advances understanding of the processes driving these phenomena. Engineering develops ever more resilient structures and infrastructure. Together, these efforts demonstrate humanity's ability to adapt to dynamic geological conditions and thrive in the presence of hazards. In the quiet of night, as we contemplate Earth's dynamic nature, we can appreciate both the power of geological forces and human resilience in coexisting with them. The ground beneath us shifts slowly but persistently, driven by heat escaping from the planet's interior. This motion generates earthquakes, builds volcanoes, creates mountains, opens oceans, and continuously reshapes the surface. These processes, playing out over timescales from seconds to millions of years, created the world we inhabit. Living with geological hazards means accepting Earth as it is, a dynamic planet where change is constant, and where adaptation and resilience allow societies to flourish alongside powerful natural processes that have operated throughout Earth history and will continue far into the future. If you found this exploration of volcanoes and earthquakes helpful for understanding our dynamic planet, consider subscribing to the channel for more calming explorations of scientific topics. A like on this video helps others discover these peaceful journeys through Earth science. Thank you for spending this time contemplating the slow, powerful forces that shape our world. Good night.